All right, now we're into section 2.7, which is density. And density, which is given by the Greek letter rho right there, RHO in Greek, is the amount of mass an object contains per unit of volume. And so you can see the equation for it is rho equals m over v, or mass divided by volume. I have a picture here that just is from your book, actually. It has a couple of different substances in there showing how density works. There's a piece of cork right here at the top floating above the water, and you can see most of it is floating above the water. We've got a piece of ice right here where just a tiny portion of it right there is floating above the water, but most of it is floating beneath the water. There's also water in there, and you have aluminum and lead. Both of those are more dense than water, so they sink to the bottom. Cork and ice are less dense, so they float in the water. This picture here is from your book as well, and it shows how the density of an object can be determined, and therefore how or what the identity of that substance is. So the first thing to do is to take any object, for example, this one here, and measure its mass. Okay, because again, density is mass divided by volume. So you use a balance to measure the mass. The volume for solid objects is measured in or by water displacement. So if you look at the picture here, you can see there's some initial volume right about here, and they have it as 35.5 milliliters. You place the object into it right there, and you can see the volume of the water increases and ends up right about here, and they have it at 45.0 milliliters. So your volume of the zinc, what it says zinc there, would be 45 milliliters minus 35.5 milliliters, and you just do the problem. 0.5, okay, there's 9.5 milliliters. So your density for zinc is going to be 68.60 grams from the balance divided by 9.5 milliliters. We have 4 significant figures in the mass and 2 in the volume. Your answer is going to be to 2 significant figures. 68.6 divided by 9.5 is 7.2 grams per milliliter. I like this picture here. It just shows a whole bunch of different substances that you can essentially lay on top of each other. They have different densities, and the density is going to decrease as you go up, obviously, because the least dense object will sit above the more dense object. And so honey would be the most dense, followed by corn syrup, maple syrup, milk, dish soap, water, vegetable oil, rubbing alcohol, lamp oil. Now if you look at it, it might seem weird. How do you get honey, corn syrup, maple syrup, and milk to do that? The reality is that they're very, very viscous, the honey and the 2 syrups. So it's actually hard to get them to mix. I've done this before. You can simply pour honey in very carefully, making sure not to get it on the sides, followed by the corn syrup. If you just let it sit, it won't do anything. If you mix it, then they will form a mixture and you wouldn't have them separated like this. Same thing with the maple syrup, and same thing with the milk. Technically, all of those things, the two syrups and the honey, would dissolve in milk, but because they're so viscous, if you're careful with the milk and you don't let any mixing to occur, it'll sit on top of it for a while. Dish soap is more viscous than milk. It also has a different polarity. It's very, very, very polar, whereas milk has a lot of fat, making it non-polar. So although with mixing, the dish soap would dissolve the milk, being careful again, it will sit on top. And look above it, even water will sit on top of dish soap. Again, there's a difference in the viscosity. This is pure dish soap, not diluted. Above the water, you've got vegetable oil. Vegetable oil and water don't mix. Rubbing alcohol is a polar compound. It will not dissolve in vegetable oil, but it is less dense than the vegetable oil. And finally, lamp oil or kerosene will not dissolve in the rubbing alcohol, and it's less dense than that. So, and they add colors to it to make it look pretty. So here's some math equations with density, or more of them. You have the equation there, rho is equal to mass over volume. Question 1 says a copper penny has a mass of 3.1 grams and a volume of 0.35 cubic centimeters. What is its density? So we just want to have the density equals what? Well, the mass is equal to 3.1 grams. The volume is 0.35 cubic centimeters. Since density is mass over volume, you get 3.1 grams divided by 0.35 cubic centimeters. Both of those have two significant figures, so your answer will be to two significant figures, and you have 8.9 grams per cubic centimeter. It actually is 8.857142787, but you have 8.85. The 5 rounds it up to 8.9. The second problem here says, what is the volume of a pure silver coin that has a mass of 14 grams and a known density of 10.5 grams? So here again, I would write the equation. Density is equal to mass divided by volume, and we need to rearrange it to solve for volume. So there's two ways you can do that. First is to multiply everything by volume. So you get rho times volume is equal to mass times volume over volume, and volume and volume cancel each other out there. So you're left with density times volume is equal to mass, and then you would divide each side by the density. So you get this. It's a bad one. There we go. Density cancels out density, and you are left with volume equals mass divided by the density. Now you just substitute the values that have been measured into that equation. You've got 14 grams divided by 10.5 grams per cubic centimeter. Your grams will cancel out, and you have cubic centimeters left over. Technically, what you would get is 1 divided by 1 divided by cubic centimeters. Anytime you have a number divided by a fraction, you might remember from algebra somewhere that you can multiply and flip that divided by fraction. So instead of dividing by a fraction, you're multiplying by the reciprocal of it. 1 times a cubic centimeter is a cubic centimeter, A cubic centimeter divided by 1 is still a cubic centimeter. So 14 divided by 10.5 is equal to 1.3, repeating, cubic centimeters, and we have 14 grams, we have 10.5 grams per cubic centimeter, so our answer needs to be to two significant figures, so 1.3. And here I have the summary of the key terms listed in your book. Make sure you know what Celsius is in the temperature scale, how to convert it to Fahrenheit or from Fahrenheit, or to Kelvin or from Kelvin. We've got centimeters, conversion factors, cubic centimeters, density, equality, exact numbers, grams, the international system of units, Kelvin, temperature scale, do all the conversions for that, kilograms, liters, mass, measured numbers, meters, metric system, milliliters, prefixes, seconds, significant figures, specific gravity, which is in the book, but I didn't cover it in the lesson, so it will not be on your test, temperature, and volume. And finally, problems in the book that I feel like you should be able to do are listed right here.